Algebra 2 students, we are going to look at the square root of -1, which is the imaginary unit I. It's an interesting history about why is it called imaginary. So just a little debrief. We have whole numbers, and then with the whole numbers, we can add the negatives, and we get integers, right? So the whole numbers feed into the integers. The integers are positive or negative whole numbers. Then from integers we can do rational numbers. Rational numbers are numbers that can be expressed as a ratio, right? See it as the first few words of few letters of rational. And then next to the rational are the irrational numbers. And the irrational numbers are things like pi, e, square root of 2, things that go on forever with no pattern. Rational numbers are repeating decimals, anything that can be written as a ratio, any fraction. Together, these make up the real numbers. Real numbers are all rational and irrational. And the square root of -1 is not real, therefore it must be imaginary. I think that's where it gets its name, but it does exist. It's not like it hangs out with unicorns and other imaginary things like your imaginary friend from when you were a kid. It's just a name. So we call the square root of -1 I. So it has this interesting property that I squared would equal -1. It's also interesting if you then think about I cubed. Well, that would be I squared times I, which is -1 times I, or negative I. And then I to the fourth, well, that would be I squared times I squared, which is equal to -1 times -1, which is 1. So this is pretty interesting. I to the first power is I to the second power -1, I cubed negative I to the fourth 1. And then it just starts over again, back at the top. I to the fifth would be I to the fourth times 1, I to the first, which is 1 times I, or I. So pretty interesting phenomenon there with the imaginary unit and raising it to different powers. Nelson, you might appreciate from a computer programming standpoint, I to the nth power, you really just need to worry about what is in percent 4. Right? So if you were to divide n by 4, this percent in computer programming gives you the remainder. So 5% 4 is equal to 1, and 60% 4 is equal to 0. What is the remainder when you do 5 divided by 4? So anyway, just a little bit of side there about I. So you may have noticed that when you are working with the quadratic formula, you often get numbers that might look like this. So here, we'll take one here. X squared minus x minus 1 equals 0. What are the factors of 1 that have a difference of 1? There are none. So what do we do? Well, we can just shortcut the completing the square. So x is equal to the opposite of b plus or minus the square root of b squared minus 4 times a times c, right? Becomes a plus because of the c, divided by 2 times a. And you end up getting 1 plus or minus root 5 all divided by 2. And if I write that as 1/2 plus or minus root 5 over 2, and then I write that as two numbers, 1/2 plus root 5 over 2, and 1/2 minus root 5 over 2. Every answer that involves a radical or an imaginary number with the quadratic formula that you've seen so far is going to look like this. And another way to write this is a plus b and a minus b. Sometimes they'll write it a plus the square root of b and a minus the square root of b. Or sometimes they'll write it a plus bi and a minus bi. And what I want you to see is whatever the solution is for your quadratic, it always ends up being in this form, a number plus a number and that same number minus a number. When that happens, these two things have a special name. They're called conjugates. Sorry. And conjugates are pretty important. They show up a lot, so it's worth knowing that term. We call these irrational conjugates. We call these complex conjugates. We'll talk about why they're called complex. Well, it just takes a second. When you put the real and imaginary numbers together, you get a set of numbers called the complex numbers. So do you see that this is a real part and this is an imaginary part? A real and an imaginary together equals complex. So anyway, conjugates are a pretty important term at higher levels of algebra. It's a pretty important idea, and you'll see how they work here in just a second. So a couple things that we want to work on now that we know what irrational numbers exactly are, which you should have known already, but what imaginary numbers are. So if we take a look, to standardize our answers, and because of a practice that is actually kind of outdated now that we have better calculators, but we still do it so everybody gets the same answers, is we do not like our denominators to have any radicals, and we don't like our denominators to have any imaginary numbers. So we do this process called rationalizing the denominator. And it's called rationalizing because it's going to take any denominator and make it a rational number. The easy examples are 3 divided by the square root of 8 and 2 divided by 5i. So in both problems, all we're trying to do is make the denominator a rational number. Most people might multiply this by 8. I'm going to show you a trick. Remember, the square root of 8 is 2 root 2. And so if I want to simplify that square root, now what I'm asking myself is, what do I need to multiply 2 by so that I get the square root of a nice number? And the answer is the square root of 2. The square root of 2 times the square root of 2 would equal the square root of 4, and the square root of 4 is a nice number. So if I do this on the bottom, I get root 2 times root 2, which is 2, and 2 times 2 is 4. But you can't just multiply the denominator by something. You have to multiply by 1. So what I've done is I haven't gotten rid of the radical, I just got it out of the denominator. And the easiest way to do that with the square root is just multiply by the square root of what it is. So if you had done this problem slightly differently and you had multiplied by the square root of 8 over the square root of 8, you would have gotten the same answer. That would have equaled 3 root 8 over 8. And then I would say, well, you need to simplify that, and that would be 3 times 2 root 2 over 8, and then 2 goes into 8 4 times, and look at that, you get 3 root 2 over 4. So it's the same way. Don't make this mistake. If you get a cube root in the denominator, right, 1 over the cube root of 2, a lot of people go, oh, I'm just going to multiply by the cube root of 2. Well, the cube root of 2 times the cube root of 2 is not a rational number. It just gives you the cube root of 4, which is still irrational. So this didn't work. You need to multiply by the cube root of 4, because 2 times 4 is 8, and the cube root of 8 is equal to 2. That was actually one of my favorite Algebra 2 final exam questions. Do you understand how to rationalize? Do you understand the idea? Alright, so that's with radicals. Let's get back to this example, 2 over 5i. So let me just clear this so we have some room. 2 divided by 5i. Well, remember that I squared is equal to negative 1, so all I need to do here is multiply by I over I. So that gives me 2i over 5i squared. Don't simplify here. We needed the I squared. That's 5 times negative 1. That's 2i here. So that's 2i divided by negative 5, and then proper form, it's usually better to leave the negative out here, so negative 2i over 5 as just a negative fraction, or you could write it as negative 2i in the numerator divided by 5. This is just bad form, so we end up writing it this way or that way. Good? One more example of rationalizing for both some more complicated radicals. So what if it was 3 over 2 plus root 5? Okay. Well, if we multiply by root 5 over root 5, we end up getting 3 root 5 divided by 2 root 5 plus 5. So we didn't rationalize the denominator. We just moved where the radical was. So if you multiply by root 5 again, you just start getting into this endless loop. So you got to multiply by something else. So let's take a break. Remember that conjugates look like this. And I'm hoping you remember that a squared minus b squared looks like this. If you go back to the factoring special patterns, I told you that the difference of squares is really an important one. And the reason why it's so important is we get to use it here. So when we take 3 divided by 2 plus root 5, we can multiply by the conjugate of the denominator, and we end up getting 6 minus 3 root 5 in the numerator. But in the bottom we get 2 times 2, which is 4, and then we get 2 times negative root 5 and root 5 times 2, so those middle terms cancel, and then I get minus root 5 times root 5, which is 5, and I end up getting 6 minus 3 root 5 all divided by negative 1, which is equal to negative 6 plus 3 root 5. And I don't know anyone that would think this over here on the left is more simple than over here what's on the right. I think what's on the right is a lot simpler and nicer. The same idea happens when you get something like 4 divided by 3 plus, or let's say minus 2i. So again, if you multiply by I, you would get 4i divided by 3i plus 2, because minus 2i squared would be minus negative 2. But you still have an I in the denominator. So you do the exact same thing. You multiply by the conjugate. Now remember, there's some implied parentheses that I'm not writing here and here. So it's not 2i times 3, it's 3 minus 2i times 3 plus 2i. And remember how you multiply that out. 3 times 3, that's 9. 3 times 2i, that's positive 6i. Negative 2i times 3, that's negative 6i. And then negative 2i times 2i is minus 4i squared. Now look, these middle terms cancel. And then you also get I squared, which is negative 1, so you get 9 minus negative 4, which ends up being 13. Now, in the top, you end up getting 12 plus 8i, and we're just going to leave that as 12 plus 8i, and we'll leave this as 12 plus 8i. I didn't do some things with rational numbers that I think imaginary numbers that I think are fairly obvious. 2 plus 3i minus 5 plus I would be 2 minus 5, which is negative 3, and 3i minus I, which is positive 2i. You just collect like terms there. I think that's pretty obvious. There's actually no way to divide complex numbers like this. You just have to multiply by the conjugate to simplify terms. So there's a little introduction into the imaginary numbers. What you need to know going forward is when you get a quadratic that has an imaginary solution. So let me just make one up. 5x squared plus 10x minus 6, or plus 6, equals 0. x equals the opposite of b plus or minus the square root of b squared minus 4 times a times c, that whole mess divided by 2a. So that ends up being negative 10 plus or minus the square root of negative 20 all over 10. You need to simplify this completely. So negative 10 plus or minus, the negative means there's an I. The 20 has a 4 in it, so a 2 comes out and a 5 stays in the middle, all divided by 10. And then the numerator has a common factor of 2 with the denominator. So the final answer is negative 5 plus or minus I root 5 all divided by 5. Good? Check my math there. I went quickly. I could have made a mistake. 30 times 4. So I think I did it right. So another answer, or another way to write this, is negative 1 plus or minus I root 5 over 5. But I kind of prefer this way, but it doesn't really matter. You wouldn't lose points for this. All right. Have a good night. Talk to you soon. Peace.